Here's my hot take. One thing everyone is seeking when they turn on their console, their laptop, or their phone and they boot up their favorite game is immersion. Even the people that get their gaming fix by doing the Wordle every day need immersion. They're immersed in discovering the word of the day and they know that they can conquer the challenge. That's what draws them in and keeps them playing. No shade towards my Wordle players, but to more serious gamers, immersion is what makes us cry when our favorite character dies. It's what gives us the courage to enter the boss room at the end of the dungeon. What gets our heart racing when we are being chased by the monster trying to escape certain doom. Immersion makes players care about these fictional characters and these fictional worlds and what makes gaming so fun. Even on older consoles with way less computational power, graphical power, musical power, video games still captured our attention as well as our hearts. And the Game Boy Advance was no different. There's an entire generation of young adults that still say Pokémon Emerald is their favorite game of all time. I was playing Fire Red and Leaf Green, but the point still stands. How did the Game Boy Advance overcome its technical limitations to make immersive games and worlds that were so captivating to people around the world? One of the most important aspects of immersive games to me is large, well-built worlds to explore, and a huge part of that is how the world is displayed to the player. It only takes a few milliseconds of a visual glitch or an issue loading the map to break that immersion. So what hardware does the GBA have to help avoid this? In its regular tile modes, the Game Boy Advance supports 4 different background sizes: a small background, a wide background, a tall background, and a large background. A small background is 32 tiles by 32 or 256 pixels by 256, while the wide and tall sizes are 64 tiles by 32 in their respective dimensions. And the large background is 64 tiles by 64, essentially 4 small backgrounds put together. I built a large background to load on the GBA just to kind of get a glimpse of what we're working with. The number in the square describes how the background is stored in memory, which is helpful when deciding what pictures to show in which corner of the large background, and the colors are pretty much arbitrary. The top left is the first in memory, then the top right, then the bottom left, and then the bottom right. And the actual screen is only 240 pixels by 160, so you can use the horizontal and vertical offset registers to explore the entire background. You can see I get from one end to the other rather quickly, especially in the horizontal direction, so not a whole lot of space even on the largest background. Definitely not enough to build an explorable world, so how do all these games do it? Voiceover Cobb here, and yeah, this episode is going to be a little bit more technical, so I'm going to talk about how the hardware works at a pretty basic level, and I'm going to use a tool to help show some visualizations of what I'm talking about. And this tool is the No Cache GBA emulator, a super helpful emulator with a bunch of awesome features like stepping through your machine code, line by line, visualizing all of the backgrounds, viewing the tile memory and the palette data. And you can easily access all of the control registers and their current values. A whole lot of good stuff from this emulator. If you are on your journey to developing for the GBA, I highly recommend this tool. I'm not going to lie, there are some quirks. It can be a little finicky with save files, and there's specific games that require a little bit more setup to make sure that they run. So having another emulator is always good. MGBA has a lot of similar debugging tools, but I still prefer No Cache GBA. If you're going to download it, I'll put the link in the description. But here on the download page, there's going to be 2 downloads. There's the gaming one, which you can go ahead and skip. That one, significantly less features, but what we're looking for is the debug version. This is going to have all of those nifty little tools to help you develop, help you learn how the games are working, and be able to view sort of the behind the scenes of those games. So that's it. I just wanted to mention that I'm going to be using this a lot for the visualizations, and we can get back to the video. Many games are able to overcome the shortcomings of the GBA display hardware with software. Let's talk about the big dog, Pokémon. You can traverse almost the entire map without ever hitting a loading zone, and all of the 5 main series Pokémon games for the GBA use the smallest background? How? Well, we learned earlier that the smallest background is 256 pixels by 256, and the screen is 240 by 160. That means there are 16 pixels on the sides and 96 pixels on the top or bottom at any given moment that are not being displayed. So after I hit a direction on the D-pad and before the character moves on screen, the GBA decides if the row or column in that direction is the correct one to be shown at that moment. And if not, it will update in those moments before the character actually moves. And this system has some synergy with the grid-based movement system. You can only go to the side or up and down, so you only need to update either one row or one column at a time. It's a pretty ingenious way to design it, but I think I could do it in my own way, which will almost surely be worse. But it's more for the sake of doing it, you know? My idea is fundamentally similar to the Pokemon method of loading new areas, but why stop at rows and columns? Why not do full 256 by 256 backgrounds? Each of the 4 smaller backgrounds has a specific place in video memory, which makes it really easy to draw each of them individually. If we allow wrapping on the large background, you can see that the colors always appear in the same order. I can create a large image of what the wrapping is doing to analyze what is actually happening. And please excuse my writing, but let's change the labels for each square from 0 to 3 to a coordinate system for each square. And remember, the color correlates to each small background that make up the large background, and a pattern starts to emerge. I'll give you a second to look for it. Again, please have mercy on my writing. Okay, ready or not, here we go. Every red square has an even horizontal coordinate and vertical coordinate. If the horizontal coordinate is odd and the vertical is even, the square is green. Vertical odd and horizontal even, blue square. And lastly, odd and odd is yellow. What that means is that based on if a background is even or odd on the horizontal and vertical axis, I can calculate which color it will be and therefore which of the 4 small backgrounds it will need to be drawn in on the large background. And it will always be drawn in that index, no matter what. All I need to do now is create a formula that takes the screen position and determines which 4 of small backgrounds from the larger map need to be drawn at any given moment. To make sure it transitions smoothly, I can use the 16 pixels and the 96 pixel difference between the screen size and the background size as an opportunity to update the backgrounds, just like they do in Pokémon Emerald. And yes, it works like a charm. The test display works really well, but that is a test in a vacuum where you might not be able to see all the flaws. I should also test it in more realistic circumstances to what a truly designed and developed game might be like. And what better environment than Earth itself? I have an image of a world map that I sloppily converted into a usable map for testing with only 2 different tiles, blue tiles and white tiles. I apologize to anyone from smaller countries that I surely butchered in this rendering. And for all you map heads out there, I see you. This is a Robinson projection of Earth. And this also works really well. No visual tearing when the new maps are loaded, no incorrectly placed backgrounds, no weird behavior when traveling diagonally. But it's important to be critical of your own work as well. And this does have some drawbacks. First of all, this is more of a proof of concept, so there were some shortcuts taken while coding that need to be improved. And there are some pretty obvious performance improvements that could be made also. And it's pretty lackluster in terms of features. It can pretty much only handle rectangular images, and it doesn't have any wrapping when you get to the edge of the world where games like Final Fantasy I or Dragon Ball Z Legend of Goku would use for their world maps. And there is a potential issue with our entire goal of the project, immersion. The system renders whole backgrounds at a time, which is much slower than one row or one column at a time. Players moving too fast, or there are a bunch of other calculations that are happening at the same time, they might see a background update, which could instantly break some immersion. But fret not. With careful considerations about the use case and some minor improvements, I think it really could be a viable option for certain games. And of course, there are so many other aspects of the game that add to that feeling of immersion as well, that are just as important to execute on to really make something great. If you enjoyed learning about how this specific feature of the Pokemon games work, or how I designed my own version, subscribe and comment if there are other cool features of your favorite GBA games that you would want to see explored next. As always, I've uploaded all of the code to a GitHub repository linked below. If you have any questions about the code, feel free to DM me on Discord at Startfling. All right, thanks for watching.